have seen that we have discussed about real numbers, we have discussed about like continuous functions, differentiable functions, and things like that. So similarly, here in complex analysis, we are going to discuss about complex numbers, and then followed by we are going to discuss about complex continuous functions on complex numbers, and differentiable functions on on complex numbers. Now the point is what you will realize soon, once we do the initial few classes, is that as far as the continuity is concerned, there is not much difference whether you think about continuity of functions of real variable or complex variable. Okay, because topologically, you are going to have a topology course also. So topologically, the set of complex numbers is just r cross r. Okay, so therefore, from the topological aspect, there is not much difference. So the main difference comes from the fact that the set of complex numbers has a field structure. Okay, and the set of the if you just think of R2 as ordered pairs, that with usual pointwise multiplication or addition, that does not have a field structure and things like that. So complex numbers have, because of this additional structure, the differentiability in case of complex numbers is slightly different. Okay, so you have I do not know if you have had you must have studied differentiability of several variable, right? Like differentiability on R2. Have you studied or not?
Yes, sir.
Yes, sir.
Yes, yesterday.
So even that, like the differentiability that we study in R2 is going to be slightly different from the differentiability in the set of complex numbers. Okay, so I'm going to explain all this. So you will see soon that the crux of the matter, or the most important point as far as the complex function theory is concerned, is that the major differences come from these differentiability properties, and that is what is going to be the heart of the course. Okay. So we will of course discuss about the structure of complex numbers and slightly the topological properties of complex numbers, but soon we will like our focus will be complex differentiable functions, and we will of course understand why these are important, and why these are so special, that we have a dedicated course for this. Why not the several variable calculus that you do on R2, that is sufficient here. Okay, so we will understand all that, and that is what we are going to do essentially. So initially, our first segment of this course is going to be dedicated towards understanding differentiable functions on the set of complex numbers. We will soon see why it is really different from the set of differentiable functions on R2, for instance. Okay, so let's begin. We are going to start with complex numbers. Complex numbers. Okay, so many of you probably have seen already the complex numbers. So it's the set C, which is like defined to be this one. So A plus IB, where A and B are real numbers, and I. You can ask me what is I. So at this moment, I'll tell you that treat I as a symbol at this moment. Okay? I have not given any meaning of I yet. Okay, so just a symbol at this moment. So as far as the set is concerned, okay, so as far as the set is concerned, this is nothing but R2. So which is set of all ordered pairs A comma B, such that A and B is in R. Okay, so that's the set, and I is, and 0 comma 1 is identified with I. Okay, so as far as the set is concerned, this is A comma 0, I is identified with the point 0 comma 1. Okay, fine. Okay, now once you have a set, you have seen that like you have had algebra courses and things like that. So you know that the moment we have a set, we want to uh, uh, understand operations on that set, mainly binary operations. Okay. Now you have additions and multiplications on R, so which make R a field. Now similarly, we are going to see operations on C, which are going to extend these addition multiplications on R, and we are going to see how it works. Okay, so if I take naturally A comma B, so that's an ordered pair, plus C comma D, another ordered pair, it's very natural to define that this is uh, define then this is A plus C comma B plus D. Okay, so it's very natural. Or for example, if I have A plus IB, and if I add another element C plus ID, we can naturally assign call it to be A plus C plus I times B plus D. It's very natural. Okay, so this is a natural addition on C. Okay, so this is natural addition on C. Okay, that's good. We get an addition, and in fact, for example, you can see that R is part of C, where you take all this. So you can imagine R is subset of C, where we take B equal to 0. Okay, so this is something which if we take, then we get R is subset of C. We can see it in this way, and in fact in that case, as a subset of R2, we identify them as A comma 0. Okay, fine. So clearly the addition that I have said, like defined over here, or the one which is natural, extends the addition that is already existing for the set of real numbers. Correct? Yes. So this one extends the addition on the set of real numbers to the set of complex numbers. Very nice. Okay, now let us define a multiplication. So we have ordered pairs A comma B, and let's multiply it with C comma D, and then the natural one that comes to our mind is AC comma BD. Right? This is one multiplication that comes naturally to us, and we can define it in this way. But what turns out, you can immediately see that with this multiplication, C is not a field. In fact, not even an integral domain. Right? Correct? So this is not a field. It's not even an integral domain. Agreed or not?
Yes, sir.
Fine, great. So therefore, if we want to have some like at least multiplicative structure on the set of complex number, this is one which is not going to work. Okay, fine, all good. Now let us try to figure out that what could be an alternate multiplication on the set of complex numbers. Okay, great. So let's try doing that. So we are going to first start by multiplying a real number and a real number with a complex number. Okay, and then we are going to see. Now the point is very simple. So I have a real number R, which is in R, and I have a complex number A plus IB, which is in C. I want to understand what is R times A plus IB. Okay, fine. Now you see, I have already that R2. If I think of R2 as the set, then R2 is a R vector space. This you already know. So now if I think of R2 as an R vector space, then if I try to imagine the multiplication that comes there, the scalar multiplication that comes there, will send R times A plus IB, A plus B, A comma B to RA comma RB. Okay, so it's very natural to set that this is okay, this is RA plus IRB. Okay, so as long as I have a real number and a complex number, I can set up the multiplication in this way. There is absolutely no problem, because this is very natural from the point of view that we see in R2, which is a vector space over R. The scalar multiplication works in this way. Okay, Fine. So I know how to multiply a real number with a complex number. Okay. So now we would like to. What do we have to understand? We will have to understand that uh, how do I multiply? For example, somewhere where I have I. So that means I really need to understand the multiplication of I with a complex number. Okay, how it works. That is what we need to understand. Okay. Now, to do that in a better way, let's try to analyze this multiplication geometrically. Okay, so what is happening here? This particular multiplication, let us try to analyze geometrically and then let us try to see. Okay, so for example, if I try to draw some picture, it will be better. So let's say I have line. So let's say I have a point. Let's say a comma b over here, okay, and I am multiplying it by r. Okay, so fine. Now if my r is something positive or non-negative, let's say even I take it r to be bigger than, so in this picture this is r is bigger than 1, so this is going to be ra comma rb to this point. And for example, if I take something negative, then when I multiply by r, it's coming here ra comma rb if r is negative. Okay. So this is how the scaling with r works. Okay. So now what we can see, for example, if r is a positive quantity, okay, then this scaling that is happening over here, that can be done as in two steps of equal scaling. Okay, so what I'm trying to say is that if r is greater than or equal to 0, the scaling by r can be done in two steps of equal scaling. Okay, so what do I mean by that? What I mean by that is very simple. Let's try to draw a picture again. Okay, so for example, if I have a point a comma 0, let's say over here, if I multiply by r, I get ra comma 0. Now I can break this operation into two steps. First, what I can do is that I can go to somewhere called root 2 r comma a, root 2 times root 2 r times a comma 0 by scaling by root 2, and then if I scale again by root 2 root r, sorry, so then I go to ra comma 0. Okay, so therefore if r is non-negative, what I can see is that this multiplication by r, I can like see this multiplication as composition of two multiplications which are of like equal scaling. So at the first step we scale it by square root r, and again we scale it by square root of r, and we get this. Okay, so similarly you can do it for any point a comma b as well. There is absolutely no difference when r is a non-negative quantity. Okay, so if I have, for example, some a comma b over here, I can multiply by square root of r. I'll get square root of r comma a, square root of r comma b, and again another square root of r, which will take me to ra comma rb. Okay, so here of course the picture shows that I am taking those r's for which r is at least 1. Okay, so or r is bigger than 1 even. So you understand that we can see this multiplication or the scaling by a positive real number can be realized by taking or like it can be seen as composition of two scalings, each of which by this quantity square root of r. Okay, now let us try to understand whether can we do the same thing in case of if r is negative. Okay, so can we say the same thing if r is negative. Okay, so if r is negative, can I visualize this operation by multiplication with r as composition of two operations which are of the same type of operations? Okay, fine. So here, exactly like scaling by square root of r, can I know, of course, square root of r does not make sense if r is negative, but nevertheless, geometrically, can I visualize the operation of multiplication by a negative number in terms, negative real number, in terms of means composition of two functions or two operations which are of which are the same operation repeated twice? Can I do something like that? Okay, so this is what is going to give us the multiplication with the complex number I. So let us see. So in particular, take r equal to -1. Okay. So I want to understand first of all what is happening over here. Great. So let us try to draw pictures again, which is the best way of to visualize things. So, for example, if I now have an a comma 0 over here, upon multiplying by -1, this is bringing me to minus a comma 0 over here. Okay, that's multiplying by -1. And similarly, if I have, let's say, something of this sort, and I have this point a comma b, and then multiplying by -1 is going to bring me to somewhere minus a minus b. Okay, so this is what, sorry, minus b, minus a minus b. I should write better, minus a minus b. Clear? This is what is happening when I'm multiplying by -1. Okay, now can you think of, just from the picture itself, can you think of means like splitting or identifying this operation of multiplying by -1 as composition of two operations, the same operations done twice successively? Can you think of anything from the picture?
Yes, sir.
Yes, what is that?
Sir, multiplying by root -1, that will
No, what is
do a
that?
rotation.
This is what I want to understand, right? But so geometrically try to think, what can I do to this number a comma 0 twice, and the same thing I'm going to do it like twice successively, so that from a comma 0 I end up at minus a comma 0. Just
Sir,
from the picture, try
90
to
degrees.
Sir, by rotating by twice.
Rotate
90
90
degree
degrees.
by two times.
absolutely very good. So what I can do here, you see, this multiplying by -1 seems to be a rotation by 180 degree, correct? Yeah. So what we can think of is that, let us try to break this operation into two operations. Again, as I said, the same operations, two same operations, each of which is rotation by 90-degree angle. Okay, so for example, I can think of that this guy is nothing but, first of all, I am going rotating this by 90 degree to a point. So what is that point will be? Tell me what this point will be upon rotating by 90 degree.
0,
0, comma a.
0, comma a.
0 comma a. And then coming here is again another 90 degrees, so it's going to come from 0 comma a to minus a comma 0. Okay, so similarly here also you can write down explicitly what happens to the, so you can draw the perpendicular. I do not know if I can draw it well. Okay, somehow the perpendicular does not seem to work, but anyway, so you can try to understand from the picture that it's going to go to some point which is perpendicular here, and then, and that's 190-degree rotation followed by another 90-degree rotation, which is going to give me this. Okay, so what we are essentially doing is that we are breaking this multiplication by -1 into two operations of which are equal, exactly the same operation, repeated twice as this rotation by 90 degree. Okay, so now let us see where does 1 comma 0 go to under this operation. So if I send 1 comma 0, this one upon rotation by 90 degree, where is it going? It's going
Zero.
to
0,1.
0.1.
0,1.
so this is under 90 degree rotation. It's 1 comma 0 is going to 0 comma 1. So this one, if I think of it as so this is of the form a comma 0, and we know that we had identified the set of real numbers as a comma 0. So what is this number? If I see it as a number in R, this one is
1.
1. And what is this number when I was trying to identify C with R2? So this number was I.
I.
So here what do I see? Under this rotation by 90 degree, 1 is going to I, something called I. Okay. So therefore, let us set multiplication by I to be the rotation by 90 degree. Okay, so this is what we are going to set that now that 1 is going to I, so let us call this rotation by 90 degree to be multiplication by I. Okay, so therefore let's see how it's going to work out for a general point a comma b. So if I take I times a comma b, so what I am going to do, I am going to understand it better, let us try to write it in a different way. So let us write I times, I know what it is as far as the addition is concerned, so I can write this as a comma 0 times plus 0 comma b. So this is I times a comma 0 plus I times 0 comma b. And tell me, where does a comma 0 go to upon rotation by 90 degree? It is
0.
and
0,
0 comma elements of the form 0 comma a are going to upon rotation by 90 degree. Just look at the picture.
Minus a comma
minus
0.
b,
B,
0.
0.
So therefore it's going to minus b comma 0. So in general, I am, when I add these two, I am going to get minus b comma a. So therefore, now I have got this multiplication by R I, which tells me if I take any ordered pair a comma b, then if I multiply with I should get the point minus b comma a. So this is the point which I did not write at this moment. At that moment, this is minus b. This is the point that I have over here, and that is obtained by rotating my point a comma b by 90 degree. Okay, and this is what we are going to take as multiplication by I. Okay, so in general, so that was by I only. So I times R of a comma b, this is said to be minus rb comma ra. So of course you can multiply the r first or the r later, doesn't matter, but nevertheless this is what we are going to get. Okay, so therefore if I have to multiply, for example, have to multiply a plus ib, and I'm going to multiply with c comma d. Okay, so bear with me because here I am using two different notation at the same time, but that's only for ease of understanding. Okay, so if I'm multiplying a plus ib with c plus id, so let us write it as c comma d. So then this is a times c comma d plus ib times c comma b, which is ac comma ad. Plus, now when I multiply by R, IB, I know this works as minus BD, comma BC. So when I add them component wise, this is AC minus BD, comma AD plus BC. Okay. So therefore, what I get is that this one is the multiplication of complex numbers, or I can say that A plus IB times C plus ID is AC minus BD plus I times AD minus BC. Okay, so that's number one. And also we notice another thing, that if I take 1 upon 90 degree rotation, it's going to I. and if I give another 90-degree rotation, it's going to minus I minus 1. So therefore, it turns out that so multiplying by I is taking you to I 1, taking 1 to I, and then when I multiply again I to I am getting minus 1. So that implies I square is equal to minus 1. So this is what we are getting, that when I am taking this complex number I and when I am multiplying I to itself, I am getting minus 1. Okay, so if you of course use the this I square equal to minus 1, again you are going to get this one. If you just multiply a plus ib with c plus id as just let's say polynomial in I, so you can just treat them as polynomial in I and you can try to multiply, you are going to get exactly this expression. Okay, so these are the same, there is no difference at all. Okay, so, so this is exactly the multiplication that we get. Okay, so this is the complex multiplication that we wanted, and it seems to uh, like have a different definition than pointwise multiplication. Okay, so now I will leave an exercise for you, show that c plus dot is a field. Okay, so dot is this dot, so the dot is this dot that is in the box. Okay, so therefore we now understand what is the multiplication in the set of complex numbers. Correct? Clear? Okay, so of course
Yes.
Yes, sir.
I could have told you in the very beginning that this I is some number. You remember when in the definition I told you at this moment just treat I as a symbol. I did not give any meaning. So at the very beginning I could have told you that okay, I square is equal to minus 1, and therefore you just take I square to be minus 1 and then try to multiply a plus ib and c minus id, and then you could have done that and you would have got this one. Okay, but now you know why I square is minus 1 and what is exactly behind all this, right? So we understood that as we saw, if I identify I with 0 comma 1, then I am getting that under the rotation of 90-degree 1 comma 0 is going to 0 comma 1, so therefore 1 is going to I. So now if I just identify that multiplication by I as rotation by 90-degree, then I see that upon giving another rotation I is going to go to minus 1. So therefore if I multiply I with itself, I am getting minus 1. So therefore I square is minus 1. So now geometrically it's very clear that how this multiplication with I works, and how we have this structure of complex numbers. Clear? Fine. Okay.
Yes, sir.
Now, just to tell you one small notation. So if we write z as a plus ib, here we take a as real part of z, and like here a is denoted. Let me write a is denoted by like real part of z, and b is denoted by imaginary part of z. Okay, so this is how the notation works. So the real part of the complex number is denoted by rez, and the imaginary part of the complex number is denoted by imz. Okay, fine, great. Now I'm going to do something else. I'm going to also tell you something called matrix representation of complex numbers. We have already seen these multiplication and all that. It is very relevant in this context to tell you about matrix representation of complex numbers. Okay, so why it is important we will see later. Okay, but nevertheless I will tell you how to treat a complex number as a 2 cross 2 matrix over R, and again you will see that the multiplication is going to come out very naturally. But nevertheless, we are going to see some very important feature called Cauchy-Riemann equation satisfied by holomorphic functions or complex differentiable functions. And at that time, you will see that the Cauchy-Riemann equation is going to come out just in one line. Okay, we will see when it comes, but nevertheless, at this moment, even from the perspective of multiplication of complex number, this matrix representation is quite useful. Okay, so what did we saw? Like what did we see? We saw that if we take AB times CD, we were getting AC minus BD, comma AD plus BC. So this is what the multiplication of complex numbers like was looking like. Okay, so therefore I can say that C comma D, if I just think of multiplication by A comma B with this map, so it was going to AC minus BD comma AD plus BC. It was going to this point. Okay, so I want to write this in terms of columns. I want to write it in columns. So it's like C column D, the column CD is going to AC minus BD and the column AD plus BC. Okay, and lo and behold, look at this one. I can write this column as A minus B, B my A times CD. Okay, so therefore what I understand is that this multiplication by A comma B, when I write, it was we were writing in pairs, so in a row. But if I try to write in terms of columns, because as I said, I'm going to do this matrix representation. So the column C comma D is going to AC minus BD and AD plus BC, and this one I can see that this is nothing but A minus B times B minus A minus B, B A, this matrix multiplied with the column C comma D. Okay, so therefore what we do, therefore we associate A plus IB, or you can think of AB, whatever you want, in C with the matrix A minus B, B A. Okay, I'm going to associate my complex number A plus IB as A as the with the matrix A minus B, B A. Okay, so in fact, if you consider the following subset of R2, so consider the following subset of not R2, M to R. M to R means set of all 2 cross 2 matrices over R. So what is that subset? I'm going to take all these matrices A minus B, B, A, such that A and B are in the set of real numbers. Then we see that what do I see if I take this set of matrices? Now let's try to examine what is the multiplication over here. C minus D, D, C. So you know how to multiply two matrices. If you do that, what are you getting? AC minus BD, then minus AB minus BC, and then here AD plus BC, and again I am getting AC minus BD. Correct? Yes?
Yes,
So
sir.
you see what is this part? AC minus BD. This is what? This is the real part of the
Real part.
real part. When I multiply A plus IB with C plus ID, whatever I get, this is the real part, and this is the imaginary part, right? Real part, and this is the imaginary part. Okay, and of course this is the minus of this term is the minus of the imaginary part. Anyway, so therefore you see that the multiplication that we had seen in the set of complex numbers, they come very naturally. In fact, if you identify your complex number a plus ib as these matrix, this particular matrix a minus b b a, then if I just multiply two matrices using our matrix multiplication rule, then I exactly get the multiplication that is coming that is there already in the set of complex numbers. Okay, so therefore we can, in fact you can see that this subset that I have written over here, a comma minus b b comma a, this particular set of 2 cross 2 matrices, they actually form a field. Okay, so this is, although m2r with respect to multiplication is not commutative in general, this particular set is going to be commutative, and whenever at least one of a and b is non-zero, you are going to get that this matrix is invertible, because that's clear, because here the determinant is a square plus b square. So the matrix is going to be invertible the moment at least one of a and b is not equal to 0. And so this particular set is identified with the set of complex numbers. So we can therefore identify C with the above set. Okay, fine. So is it clear, this part? Yes.
Yes, sir.
Yeah.
Yes, sir.
Okay.
Yes, yes, clear.
We
Yes,
can
sir.
find the set of complex numbers, these set of special 2 cross 2 matrices. Okay, so remember this point. I am going to revisit this again. As I said, you will see when we talk about CR equation, you will see how this is going to be very like the CR equation is going to be just a simple like will immediately come from this one. Okay, fine. Anyway, so we will see it later. So nevertheless, let's keep it like this. Okay, now I have something called polar representation. Okay, so we had matrix representation. Next thing is that polar representation. Again, many of you might have seen this. This is very standard. So I have already told you that the set of complex numbers, we were seeing it as R2, and therefore and R2 is a vector space over R. So already means I'm talking about vector spaces. So when you think of vector in the sense of like vector calculus that you have done, so generally what does vector entail? So they entail, for example, if I talk about a vector in R2, it's going to entail some modulus and a direction, correct? Yes, when I think of a vector, then what comes to our mind is a modulus and a direction, isn't it? Okay,
Yes, sir.
so that is exactly what polar representation of complex numbers is all about. Okay, so let's say we have, so let's try to draw a picture. So let's say I have a point a comma b somewhere here. Okay, and let's say this is a comma b, and now what is this height? So if I try to draw the picture again, let's start from here. So this point is a comma 0. So this distance is a, and this distance is b, of course. And so if I think of this one as a comma b as some vector, so therefore this quantity implies, gives you the modulus of the vector, and this angle theta gives you the direction. Okay, so now what do you mean by modulus? By modulus you just mean distance from the origin, right? So we have, let's take a and b. So this one is treated as a vector, has modulus What is its modulus? So as I said, it's the modulus is the distance from the origin, and this is nothing but square root of a square plus square, right? That's the distance, correct? So that's the modulus of the complex number a plus ib, we can set. So we set that mod z is equal to square root, this is positive square root of a square plus b square, where z is equal to a plus ib. Okay, so this is what we have. And as for the direction is concerned, for the direction, we have this, I can say that tan theta, for the direction tan theta is given by b by a. Okay, so that's how we get the direction. Okay, now of course, how do I get theta out of tan, like out of this equation? So I can take tan inverse, but you already know that sine tan, so none of these are for example, what do you call, these are not injective functions, so therefore I might have several choices for theta. Okay, so for example, if you have one particular choice of theta, then theta plus 2 pi will also be a choice for theta. For example, if I have some theta 1 for which tan theta 1 is b by a, then if I take tan of theta 1 plus 2 pi, that is also going to be b by a. So similarly, if I take tan of theta 1 minus 2 pi or minus 4 pi or plus 4 pi, whatever it is, I'm still going to get the same b by a. Okay, so if I want to really think of this direction, um, what do you call this theta, so we will have several choices. Okay, so what we are going to do, we are going to restrict ourselves to one particular segment of thetas or one particular set of values of thetas. Okay, and those are the things which we are going to consider as the uh, angle. Okay, so let me write as tan is not an injective function, we will take thetas, we will, or we will consider theta to be having values in the interval, let's say what do I want? So when I do the logarithm, I don't want to remove this line, so maybe I can put for this for the moment minus pi, or actually, okay, so anyway I can put it anything, but when logarithm comes I will see. Okay, so let's put it like this. Okay, minus pi to plus pi. uh, Here one side close, one side not so close, but okay, I might have to see, for example, yeah, so yeah, okay, so this is fine, this is fine. So I'm going to, anyway, I'm going to exclude this pi at some point of time, but anyway, so we are going to take values of theta in this range, and this is called, or this value of theta will be called the principal,
Principal.
yeah, principal argument of z. Okay, so we are going to denote and denoted by, denoted and will be denoted by argument of z. Okay, so argument with a capital A. Okay, so often argument is written with little a, so when I am talking writing as capital A, so I am saying that the argument is lying between minus pi to plus pi, Of course, I need to keep it closed at one point, so I'm keeping it closed in towards pi. Okay, so this is called the principal argument. So now that I have this, so how can I represent my complex number, for example? So now that we have now that we have these two concepts, so here I have mod z and I have theta. So now that we have mod z and theta, so mod z is often written as r, but anyway, so let it be. So we have, so what is cos theta? So for example, if I take a by mod z, this one is cos theta. And if I take, for example, here a by mod z is r. So here I have reset. Okay, so let me write r here. So now that we have this r and theta, we have a by r is equal to cos theta. Similarly, b by r is going to be sin theta, is equal to sin theta. So we have a comma b is same as r cos theta and r sin theta. Okay, so where r is the absolute value, and so therefore you can think of writing it as for example, uh, so if I try to write it as a plus ib, it will be r cos theta plus I times r sin theta, and so which is r of cos theta plus I sin theta. And you know the power series expansion of cos theta and sin theta, so if you add them up you get r into e power I theta. Okay, so if you just substitute those mm, power series expansion of cos theta and sin theta, you get this one. And so a plus ib can be written as r e power I theta, where r is the uh, absolute value and theta is any argument will work, but let's take the principal argument. Okay, and this form is called the polar representation of complex numbers. Okay, so you know what is r? R is square root of a square plus b square, and theta, you know, this is tan inverse b by a, right? Yeah, tan inverse b by a. Of course you are going to take, you can take, for example, when you write r e power I theta, you can take any theta. You don't have to really take the principal argument. Even if you translate it by another 2 pi or 4 pi, doesn't matter really. But in general, when we talk about principal argument, we are going to take between minus pi to plus pi. Okay, so fine. Is it fine so far?
Yes, sir.
Yeah.
Yes, sir.
Yes.
Yes, sir.
Now
Yes, sir.
if I have this polar representation, then of course multiplication becomes very convenient. Okay, so you can just a plus ib times c plus id. If a plus ib is r1 e power I theta 1, and c plus id is r2 I theta 2, then a plus ib times c plus id will just be r1 r2 e power I theta 1 plus theta 2. Okay, very simple. Okay, great. So this is what we have, and I just need to set few more notations. Okay, so which are going to be useful for us. So notations. So we have had this real part, we have had imaginary part. Now we also had this absolute value, and we had argument of z. Okay, so another important thing that comes up naturally. So this you must have done several times while calculating roots of a real polynomial. You have often got complex roots, and you had seen that complex roots appear in pairs, and the pair was nothing but the conjugate pair. Okay, so what was conjugate pair? So z, if I take z equal to a plus ib, then if z equal to a plus ib, then z bar, which is defined as a minus ib IB is called the complex conjugate of Z. Okay, so this is a simple definition. So if you have a complex number a plus ib, its complex conjugate is called a minus ib, which is z bar. And like for example, the real part of z and z bar are the same, whereas the imaginary part of z bar is nothing but minus of the imaginary part of z, and so on and so forth. So these things are very easy to understand. And for example, we have mod of z square is nothing but z into z bar. Okay, so all these are very trivial observations that one can have. And similarly, you can in fact represent your real part as, I think, z plus z bar divided by 2. Similarly, your imaginary part would be, I think, z minus z bar divided by 2i. Okay, so these are some basic exercises about the conjugate, and some other properties which I can list down. For example, if I have two complex numbers z1 plus z2, taking its bar is same as z1 bar plus z2 bar. And then, for example, if I take z1 z2 bar, its complex conjugate of z1 z2 is product of each of the conjugates. And also, for example, the absolute value of z and z bar, they are the same. So these are the some basic facts about complex conjugates that we have. Okay, so this you already know. Okay, so I don't want to start something new today. Next thing that I have to do is called stereographic projection of the set of complex numbers. Okay, so the set of complex numbers can also be seen as part of the unit sphere. Okay, so there is a way to compactify. So I do not know, some of you know this or not, but like in R, you must have seen R is not compact. So R2 will also not be compact. So as a topological space, R2 and C are the same. So C is also not compact. Now there is a way to compactify this. The whole of complex plane, it's called one point compactification, and you get a sphere. Okay, so in the sphere, except the north pole, you can decide which point you want, but generally it's taken to be the north pole. So except the point which is in the north pole, except that point, all other points can be identified. Can It's possible to identify all other points of the sphere with complex numbers in a bijective way. Okay, so therefore, if you imagine a complex plane, that's if you imagine a plane, and on top of that, if you imagine a ball or a sphere, then except for the point which is on the top, that is the north pole, you will be able to associate the set of complex numbers with the points on the sphere. Okay, and so actually these associations come from the one projection which is taken by, for example, you take any point on the sphere which is not the north pole, and then you draw the line joining the north pole and that particular point. So that's going to hit somewhere in the plane. Okay, so I will draw the picture in the next class, you will see. So if I do that, then what happens is that I get that I can identify my set of complex numbers with the punctured sphere, like except the north pole. And this identification is something called the stereographic projection. Okay, so we have to see, I will have to write down some formulas regarding that. I have to tell you what are the points, how they are going to get associated and all this. Okay, so that's called the stereographic projection, which we are going to see in the next class, and we are going to take it from there. Okay, so I hope to finish this topological aspect of complex numbers by the next class, and then we are going to start the differentiation from next week. So let's see. I would like to finish this by Thursday, and then we will start differentiation, which is the most important thing I have already told. Okay, fine. So I'm going to stop here. You can tell me if you have any question.